Here are solutions to homework set number 11 for ECE 461 control systems. For this homework, we're going to look at the 10th order heat equation. This is a 10-stage RC filter, or just keep the 4 dominant poles and treat that as my system. Come up with a digital controller for this system to meet your design specs, and also assume a 0.1 second sampling rate. Now the first problem is design a digital I compensator. So with an integrator, I have this form of the compensator. It's z over z minus 1 times k. Pick k to give you 20% overshoot in the step response. So in that case, there's a couple approaches. I can convert g of s to the z-plane, draw the root locus in the z-plane. I've got 4 poles in the z-plane. These come together, split apart. Draw in your damping curve, find out where they intersect, and pick k to make the gain 1 there. What I'm going to do is a numerical approach. I've got g of s, a zero-order hold. That's the sample and hold. That's basically a half-sample delay to model the zero-order hold, times k of z. I'm going to search along the damping line and the s-plane. That's search along the zeta line for 20% overshoot. That's 0.4559 for zeta. Search along that line till the angles add up to 180. At that point, make the gain 1. And the kind of way that works is there is a root locus. It does cross this damping line somewhere. I don't really care about the rest of the root locus. I just care about this one point. In addition, what's nice about it is I don't have to convert the g of s to the z-plane. I can model the sample and hold almost exactly. I've got k of z. The fact that I'm mixing planes doesn't really bother me. Once I know s, I know z. Again, z is e to the st. I know s from a damping line. I know t, 10 milliseconds. I can find z. So when I do that, I'm going to search until the angles add up to 180. And it turns out the solution is that s is minus 0.48 plus j 0.97. Z is 0.94 plus j 0.009. That's related by e to the st. If you multiply all this out, I then get 180 degrees, which is good. That's the point on my root locus plot that I care about. The gain's wrong. Pick k to make the gain 1. So k should be 0.1289. And MATLAB, I can find that. Here's your g of s, there's s, here's t, there's z. Evaluate g of s at that point in the s-plane times the half sample delay for the sample and hold times k of z. So I need to know z given s. And I want the complex part to be 0, or I want this to be negative real. So this point is not on the root locus. Keep iterating, make it 10% larger, keep going, keep iterating until the complex part is 0. At that point, I've got the spot on the root locus plot, s and z. To make the gain 1, pick k to make the gain 1. The ask to test is, does it work? If you have VisSim or Simulink, I can simulate it. Here's my discrete time compensator, sampling rate 10 milliseconds, and you can see that with the stair steps. Here's my g of s analog. Put these two together, and sure enough, I get 20% overshoot and no error. The no error is guaranteed because this is a type 1 system. So that was problem number 1. Problem 2 says now do a PI compensator. The difference between I and PI is with a PI I get to put a 0 anywhere I want, versus the integrator, I stuck the 0 at the origin. If I do that, I can use the 0 to cancel the pole at minus 1.21. Converting the z-plane, z to the st, I put the 0 at 0.886. That cancels the pole at minus 1.21 in the s-plane. Now repeat. I've got the form of the compensator. Now pick k for 20% overshoot. And again, I'm going to do a numerical search. Search along the damping line in the s-plane. That's your 0.4559, 20% overshoot. Search along that line till the angles add up. So if I guess minus 2 plus j4, that's wrong. Make it 10% bigger. I'm going in the right direction. 10% bigger, better, better. Eventually, I get the complex part to be 0, which is what I want. That says this point, whatever it is the point on the damping line that intersects with the root locus plot. That point was minus 2.5 plus j 5.18 in the s-plane, 0.66 plus j 0.3 in the z-plane. Again, z is e to the st. To make the gain 1, Pick k to make the gain 1. So k is 4.004. Here's your k of z, and the acid test is try it. Put it in your system, and I now get a quicker system. Again, before the settling time is like 5 or 6 seconds. Now it's right around 2 seconds. And again, see the input u is discrete. That's the blue line. 20% overshoot, no error. That's a valid design. Problem 3 says design a PID compensator. Now in the z-plane, PID means proportional integral delay, not derivative. So here's my delay of 1 over z. There's my integrator. I've got 2 zeros to put anywhere I want. Pick those 2 zeros to cancel your 2 slowest poles. So the pole at minus 1.21 goes to 0.88. The pole at minus 9.02 goes to 0.405. So there's my zeros. I've got the form of k of z. Now do a search. Where on the damping line do the angles add up to 180? So searching, searching, searching. Eventually wind up, okay, it's at minus 3.7 plus j 7.4, S-plane. Z-plane, z is e to the st. There's your spot in the z-plane. Pick k to make the gain 1. At that spot, it's negative real, which is good. The gain's wrong. Pick k to make the gain 1. So k is 8.48. So there's k of z. And the acid test is try it, and I should have 20% overshoot. It's close, a little bit off. No error for step input, a little bit faster. Probably just didn't quite get that to enough decimal places. But that's problem 3. Problem 4 is more of a generic design. Assume a sampling rate of 0.1 second. I want to have a 2-second settling time and 20% overshoot. Come up with k of z. Well, to do that, it's kind of what we did in the S-plane. I'm going to cancel the pole at minus 1.2, minus 9.02, add a pole at s equals 0, that makes it type 1, add a second pole, slide this guy around until minus 2 plus j4 is on the root locus. Z-plane, same thing. A pole at minus 1.21 is 0.886 with t is 0.1. Here's the second 0, here's the pole. The second pole I don't know where it is. So let's evaluate everything that I know. I know g of s, the half sample delay, k of z, ignoring the stuff that I don't know. Do that, and the angle's wrong. It's at minus 130 degrees. I want it to be minus 180. That tells me the angle to the pole. So here's my design point right here. This angle to my pole is 49 degrees. Find that pole. That's a little bit of trig. It's 0.75, the real part of z, minus the complex part over the tangent. A little bit of trig. So this point right here, complex part is 0.31, real part's 0.75. I'm going to go left of 0.75 by this distance. Or in MATLAB, it's the real part of z minus complex part of z over the tangent of 180 degrees minus the angle. So A is 0.48. As a check, evaluate g of s times half sample delay times k of z, all that right there is k of z, at your design point, and it's negative real. That's good. That says I picked this point right. Pick the pole right. Pick k to make the gain 1, and there's k of z. Acid test is try it. Throw it in here. I've got 20% overshoot, a 2-second settling time, no error for step input. This compensator meets my requirements. The last problem on the homework is suppose I change the sampling rate. Now modify k of z to accommodate the changed sampling rate. So this is kind of where you grumble, because if I change the sampling rate, that basically means take the previous design, throw it out, start over. So changing the sampling rate is a big deal. So basically I have to start over. I want to cancel the poles at minus 1.2, minus 9 in the S-plane, convert to the Z-plane. If t changes, the zeros change. Add a pole to the origin. The second pole, I don't know where it goes. My design point is now minus 2 plus j4 S-plane, no change. Z-plane, this does change because t changed. So let's evaluate everything that I know. I don't know A, I don't know K. Evaluate everything else. So there's G of S, half sample delay, here's your K of Z, at least the stuff that I know. Analyze it, and the phase is wrong. I need to have an extra 53 degrees phase shift, so take your point that you're designing at. I need to go left, here's your pole, and that angle is 53 degrees. And MATLAB, that means take the real part of the pole minus the complex part of the tangent. A is 0.1167. So this right here is your K of Z. Analyze at my design point, minus 2 plus J4 in the S-plane, whatever it is in the Z-plane. And that worked. Complex part is 0. So this is negative real. That point's on the root locus. Pick K to make the gain 1. And here's K of Z. And if I check it, here's your K of Z. You can now see a 200 millisecond sampling rate, 20% overshoot, 2 second settling time, no error for step input. That's also a valid compensator. Very different than the previous one because I changed the sampling rate. I change pretty much everything. But that's homework set number 11 for ECE 461. Maybe.